And you will find that this extra sum of squares method is actually a special case of testing general hypothesis. Okay? So that's what I want to do today. So let's let me have a brief review of extra sum of square method. This one. Well, what it is that we have a model here, y equal to x1 beta 1, x2 beta 2. So what that means is we already have a model. Yeah. So we have this smaller model called a reduced model, and then we want to investigate whether we should add some more regressors to the equation or not. Because if we leave out any useful regressor variables, that won't be good. Yeah. We want to include as many as possible regressors that are useful, and at the same time keep the number of regressor variables minimum. The more the bigger the model, the more complex it is. We want a small one, yet it includes all the useful variables. Yeah. So can you hear me at the back? Yes? Any problem at the back? Can you raise your hand if you can hear me? Can? Okay? Yeah. You need to speak out if you can't hear. Don't sit there in pain, okay? So, I want to test whether this beta 2 is equal to 0 or not. I want to test whether we should include this part or not. See, if beta 2 is 0, then we shouldn't be using the full model, but rather the reduced model. So the statistics that we use is this. The denominator is always the residual mean square. So, but the numerator is SSR beta 2 given beta 1. So what is this quantity here? Well, this quantity is the extra sum of square due to the introduction of beta 2. So I have given you a formula here. According to our notation, SSR beta 2 given beta 1. It's the sum of square regression due to all the betas, subtract sum of square regression due to beta 1 alone. So we are trying to find out whether this introduction of beta 2 will it cause a big increase in the regression sum of square or not? If it causes a big increase in the regression sum of square, then beta 2 is useful. If you introduce beta 2 and these two are quite similar, it causes a slight increase, then beta 2 is useless. Then we will then stay with the reduced model. So that's the idea of extra sum of square method. So today I'm going to talk about testing general hypothesis, linear hypothesis about beta. And it will become clear very soon that this extra sum of square method is just a special case of this one. So let's have the usual setup. So let's just go through that. So number one, suppose we have a full model. You can see that the number of parameters is P. P includes the intercept term, beta naught. So beta naught, beta 1 plus 2k, and P is k plus 1. So here's our multiple linear regression model. Expected value of the error vector is 0. The variance is sigma square in. So the diagonals is all sigma square. And the off diagonals are 0. So we know that all the y's have covariance 0. And if you look at a multivariate normal distribution, covariance equal to 0 means they are independent. This result is not true in general, but for multivariate normal, covariance is 0 means independent. Okay, so what do we want to test? So we want to test this. We want to test linear, some linear combinations of beta. So let's just say T is R by P matrix. Now this is R by P. This is P by 1. So this 0 vector is R by 1. So we want to test R linear combinations of beta. Okay? And I'm going to assume that the R equations are independent. So if you read the book, I think the book gives you a slightly more general setting, which I find a little confusing. That's why I'm writing my notes here to help you to understand it. Alright? Because if there are equations that are not independent, you can always remove it. So, I hope my explanation here will be clearer than the one given in the textbook. So let's just assume that all these R equations are independent. Now an equation, any of the equation is just a linear combinations of the betas. So what does that mean? I think it's easier to understand this T matrix if I illustrate with an example. It's not good to keep talking about theory and theory. You won't understand, or at least most of you. That's why I didn't put any of the theories in the class. So you may think I skip the hard part, but actually not. I leave the hard part to you, for you to work out during tutorials. Okay? I am not moving away from hard part, fortunately. But I don't have to do it myself. You do it. So let's look at an example to understand this matrix T. So my model is here. This is my model. there are 5 regressor variables. So there are 6 regression coefficients. And I want to test this. See, I want to test whether beta 1 is beta 3, beta 4 is 0, beta 5 is 0. So this is called general hypothesis on linear combinations of beta. What does that mean? Well, for example, this hypothesis can actually be written as this. This hypothesis here can be written as this, where the matrix P is defined here. So if you look at the first row of P, you find that, this is, when you multiply T by beta, see, you'll be multiply this by beta naught, beta 1, beta 2, beta 3, beta 4, beta 5. So the first equation, you are going to get beta 1 minus beta 3, and that is equal to 0. Now the second linear combinations of beta is given by the second row of T, which is here. So this is, this row multiplied by beta, the vector of beta, you get beta 4. And then the last row is beta 5. When you multiply, T by beta. So when you multiply this, so basically what you have, your matrix, let me just write down the matrix, the vector. So what is TB? TB is beta 1 minus beta 3. T times beta, the second row will be beta 4, and the third row is beta 5. And I want to test this. So this is T times beta. So you can see that T matrix we can figure out easily. And is, when you multiply by beta, you will get exactly what we want to test. The first line tests whether beta 1 minus beta 3 is equal to 0 or not. In other words, whether beta 1 is equal to beta 3. Second line shows that we want to test beta 4 equal to 0. And then the third line tests beta 5 equal to 0. So it's exactly the same as this one. See? It's exactly the same. So, in other words, writing this is the same as writing this. Can you understand? It's just that I'm using a matrix notation to denote it. Now, each element of TB, T beta, is just a linear combination of the betas. That's why this topic is called testing. It's called general linear hypothesis about beta. Yeah. General means it can be anything, but it has to be linear. Alright, so that's what we have now. So that's point number 1 of my notes. So that's point number 1. So you follow the point, one point at a time. You'll be able to understand my lecture notes better. you read the book, it will be harder, at least for first timer. But after my notes, I guarantee you that the book will be much more friendly. Alright, part 2. Part 2 is we apply this set of constraints on beta, linear constraints, onto the full model. And we will obtain a reduced model. Alright? So, that's the theory. Sometimes hard to understand this statement. What do you mean applying this, you get a reduced model? So again, if you look at an example, it will become crystal clear. So for that example, let's try to apply the constraints, that means applying this beta 1 equal to beta 3, beta 4 equal to 0, beta 5 equal to 0 is the same as applying 3 times beta equal to 0. They are identical. Okay? So how do we apply? Well, let's take a look. So here is our full model. I've already applied it. Beta 1 stays the same. Beta 2, no change. Beta 3 is now beta 1. Yeah? And then beta 4 is 0. Beta 5 is 0. And so I can group this and this together to have this. So now I have a smaller model. And I can relabel them a little, because this beta 1 has no longer the same meaning as the beta 1 in the full model. Why? Because they are different models. Okay? They don't have the same meaning. So I can call this gamma naught. In fact, these two beta naught are also different. Now, this is gamma 1. x1 plus x3 is z1. Beta 2 is this one. x2 I call it z2, as I have written there. So now you know that we now have a reduced model. Okay? So apply this to get a reduced model. So that's point number 3. So to test this, T beta equal to 0 versus T beta not equal to 0, we consider these two models. Y equal to x beta plus epsilon, that's our full model. By applying T beta equal to 0 to the full model, we get the reduced model. So the reduced model, for example, is this one. So here's our reduced model. This is called Z tau plus epsilon. So this matrix, the reduced model, is y equal to z tau, this tau, capital tau, plus epsilon. So these two are the same. So for the example, so it's easier to understand if you refer to an example. Our full model, there are 5 regressor variables. And after we apply the 3 constraints on beta, linear constraints on beta, we obtain the reduced model as shown. Okay, so so now, how do we go about testing this? How do we go about testing this? Well, surprise. The SSH that we can use to test this set of constraints on beta is given by SSH, which is the reduced sum of square, which is the residual sum of square of the reduced model minus the residual sum of square for the full model. Yeah? It's just like the extra sum of square method, right? It's the same. And the degree of freedom is R. The degree of freedom, look at this carefully. This is R. R, where did we get R? It's the number of constraints on beta that we are trying to test. This is important. So let me go back. It's here. So R refers to the number of rows in P, which is the number of constraints of beta that are independent, of course. So R refers to the row dimension of T. You know, how many betas are we testing? How many, not beta, how many constraints are we testing? So in this example, we are testing 1, 2, 3. We are testing 3 constraints. So in this case, R will be 3. So R, for our example, is 3. Alright? Well, what about the F statistics for testing this set of constraints, linear constraints on beta? Well, it's given by this F statistics here. Again, this is based on linear model theory. Some of this you will prove it in the tutorial. Some of it I have already asked the student to do it in the final exam. So you have to be good in theory if you want to get an A+ or A. So the F statistics for testing this is given by this. Note that the denominator is always the same. It's the residual sum of square of the full model divided by n minus p, or the mean square residue of the full model. Now, the F statistics, the numerator is SHH over R, and you reject if F is greater than the upper F percentile. So according to my notation, this is alpha, this quantity will be this. So this is the PDF of the F statistics. And the degree of freedom for this F statistics is R. The second degree of freedom is n minus p. N minus p refers to the degrees of freedom of the residual sum of square. R refers to what? The number of constraints that you are testing, number of independent constraints of beta that you are testing. In this example, it is 3. So we don't figure out from here. We figure out from what we have deleted from the full model. Okay, so let's look at an example. So this brings us to point 6, which is an example. Now this PR2103 data, I collected it from a class of mine. These are pharmacy students taking statistics. So I collected some data from them about their blood pressure, heartbeat, religion, race, and so on. So here I'm using this data for illustration. Well, so in this case, I am actually using the 5 regressor variables for this data set. And by the way, PR2103 is the name module code for that course, all right? In case you wonder why it's called PR2103. All right, so I want to test whether, now, the example, I test whether beta 1 is 3, beta 4 is 0, beta 5 is 0. So my full model is here. Maybe I just write in short. This full model. This is the reduced model. The reduced model is based on these 2 new regressor variables. So it's based on what? It's based on, it's based on Z1 is equal to this, X2, Z2 is X2. From our derivation, yeah, I hope you understand that. Because here, in case you do not understand, so let me just say one more time. This is Z1, this is Z2. After we apply this condition to the full model, we get a reduced model. So I have to calculate Z1 and Z2 before I can use the model, right? So that's exactly what I'm doing. So I calculated Z1 as X1 plus X2, Z2 as X2, and then I compare these 2 models, reduced model and full model. Now, what is the degree of freedom for this test? Well, we are testing 1 constraint on the betas, 2 constraints on the betas, 3 constraints. So R is 3, which is here. So if you compare these 2 models, that would be your R. And the difference of the 2 residual sum of square will be our sum of square. This is SSH. So SSH is based on these 2, which I have stated for you. So SSH is the sum of square of residue for the reduced model minus sum of square, the residual sum of square of full model. So here is the sum of square SS residue of reduced model, and this is SS residue our full model. So if you subtract these two, you will get the sum of square that will allow us to test the three. Now the null hypothesis comprises three constraints on betas. So in this case, what happened? In this case, you can see that the p-value, so sum of square, that is the f statistics, this is the f, and then that is the p-value. P-value is large. We only reject the null hypothesis if the p-value is small. So p-value is large, so there is no evidence to indicate that the alternative hypothesis is true. So in fact, there's evidence that the null hypothesis is probably true. Here, probably, because we don't have any evidence to reject this null hypothesis. All right. So that is the. So I've gone through this whole procedure with an example to illustrate how you can test general linear constraints on betas. Okay? And the next point that I want to make is that this extra sum of squares method is actually a special case of testing the general linear hypothesis about beta. Now, what is this extra sum of squares method? Well, it is testing whether additional regressive variables should be added or not. So for example, if I'm testing this, so my full model, my full model will comprise, beta naught, beta 1, beta 2, beta 3, 4 and 5. But the reduced model will only be based on beta naught, beta 1, beta 2, beta 3. So this is the sum of square that we use when we look at the extra sum of squares method. It is this one, right? So what is this one? This is, let me write down, beta naught, beta 1, beta 2, 3, 4, 5, minus SSR, beta naught, beta 1, 2, 3. So this is our full model. This is our reduced model. So in the extra sum of square method, I already have a reduced model, comprises beta naught, beta 1, beta 2 and 3. I want to test whether I should include beta 4 and 5 or not. And according to the extra sum of squares method that I described in the last lecture, this is the sum of square that we should be using, because it will tell us what is the extra sum of square due to these two, when you compare these two. So you fit a model based on the reduced one, and then fit a model based on the full model. And then look at the difference. The difference will tell you whether the contribution to the sum of square regression is small or big by adding beta 4 and beta 5. And we can write this difference compactly in this form. right here. Okay? And this sum of square that we use for testing beta 4 equal to beta 5 equal to 0 is exactly the same as SSH that I described to you today based on this T matrix. This T matrix says what? It says, the first row of T says beta 4. See, this is beta 0, beta 1. This corresponds to beta 2, 3, 4, 5. So this corresponds to beta 4. This corresponds to beta 5. So T beta equal to 0 is exactly the same as saying B4 equal to 0 and B5 equal to 0. Can you see that? And the SSH that you calculated is actually the same as what we did for the extra sum of squares method. Okay? No surprise. So let's look at an example to illustrate this idea, and also further examples on testing general linear hypothesis. So let's look at this PR2103 data again. So I have Y is the systolic blood pressure that I want to predict. I can predict it using the diastolic blood pressure, or I can use the number of heartbeats per minute, or I can use the weight. All these are useful explanatory variables for systolic blood pressure. The height, age, exam score. Hey, your exam score, is it relevant to your systolic blood pressure? Yeah? If you do well, your systolic blood pressure will always be under control when you are in my class. You're not too excited. But if your exam score is low, I tell you, your systolic blood pressure will be high. My systolic blood pressure is always low. Why? I have no exam. I said exam, I don't take exam. That's why my systolic blood pressure is always low. Did I lie to you? No, it's the truth. My systolic blood pressure is always low. Because I don't eat a lot of meat, that's why. I eat mostly vegetables. Alright? So, also I don't take exam, that's one big reason. So we are going to, I'm going to demonstrate 3 tests here. The first test, we can use the extra sum of square principle, but we can also use the method that I described here today. And then the second one is based on this. See, this is called general linear constraint. All right, this is a very special type of constraint. See, this is different. This type of constraint is different. So let's look at the first one. So here, I want to test whether should I include 4 and 6 or not in my model. What is 4 and 6? Maybe height is not so important, right? Weight, I think, is a very important factor to systolic blood pressure, because blood pressure, when you pump, when the heart pumps the blood to the other parts of the body, if your body is huge, You know, it exerts a lot of pressure on your heart. You need a bigger pump to pump, but we all are born with the same heart. So you will pump harder for someone who is heavier. For height, you know, I think it's lesser, the effect. Exam score, I think, is not so critical. So we want to test whether these two regressors are useful or not. Okay? So suppose we are happy with this already. We are happy with this. We just want to find out, should I include exam score and the height as regressors? We don't know until we test it, right? So let's do the test. So the test is very simple. This is your full model. This is your reduced model. Full model, reduced model. You can see that beta 4 and beta 6 are not here. Of course, you can relabel them as Z1, Z2, Z3, Z5, but it doesn't matter. It's all right. But note that the interpretation of beta 2 is different for the two models because they are different models. All right. So, how many constraints are we talking about? Two. Two constraints. Beta 4 equal to 0. Beta 6 equal to 0. So two linear constraints on the beta. So R is 2. And the p-value is very large. 0.4 is very large. So we do not reject H0. So we do not reject H0. So we do not reject H0 to say that this is. So we don't want to reject this. Let me see. Why is that so? In this case, we do not reject H0. So what that means is probably beta 4 and beta 6, they are 0 or close to 0. In other words, they are not useful for the prediction of Y. Now, let's go to the second case. Second case. Here, I want to test beta 1 equal to beta 2 equal to beta 3. Beta 4 equal to beta 6 equal to 0. So, can I ask you what is R here? R is the number of constraints on beta that we are testing. So, can you tell me what is R in this case? The full model is there are 6 regressor variables, and then we introduce the constraints to get the reduced model. So what is the value of R? Beta 4 equal to 0, 1 constraint. Beta 6 equal to 0, 1 constraint. Beta 1 equal to beta 2, 1 constraint. Beta 2 equal to beta 3, 1 constraint. So there are 4 constraints, but I can write it all in what I've shown you here. Okay, beta 1 equal to beta 3, beta 2 equal to beta 1 equal to beta 2, 2 equal to 3, that means beta 1 is equal to beta 2 equal to beta 3. So R is 4. So let's do it. Or you can find out using the degrees of freedom of the reduced model and the full model. Yeah, to do it. So let's try to see what it is. So first of all, we need to find these new regressors. which I call x123. x123 is to denote the sum of the three regressor variables. Yeah. And x5, I can call it z2, but it doesn't matter. You can just leave it at x1. So my full model is here. My full model and my reduced model, two regressors only, and then I can test the 4 constraints. Can you see? R is 4. Alright, so remember, R is the number of linear combinations of betas that you want to test. And of course, you can also use the degree of freedom of the full model and the reduced model to figure out what is R. So in this case, the p-value is still very large, so we do not reject H0. That means there's no evidence to indicate that the null hypothesis is true. Alright, next example. I want to test this. For some reason, for some example, you might think that beta 1 should be the average of the other two. Let's say, now, how do I come up with this equation? Well, it depends on your own domain knowledge. You work on a problem, you have a good feel. What is the relationship among them? So you figure this out. You don't just simply write down, a constraint. It's based on domain knowledge. So here I have 3 constraints or 3 linear combinations of betas that I want to test. Again, full model is this. And I apply beta 4 and 6. So this is 0. This is 0. They are gone now. Beta 1 is this. This beta 1. So I'm trying to find out what the reduced model is. So I have beta 2, beta 3 over 2. And then of course I need to combine all the beta 2 and beta 3 together. So this is the new regressor variables. So there are only 3 of them now in the reduced model. And I call the 3 new regressor variables Z1, Z2, X5. Yeah, X5 stays the same. Where Z1 is this and Z2 is this. You got it? Okay, so let's do it. So I find Z1 first, Z2, and then fit the full model here, reduced model. And then, in this case, R is 3 because there are 3 constraints. 1, 2, 3. 3 constraints. So R is 3. And in this case, the p-value is very small, so I reject the null hypothesis. And so there's evidence that the alternative is true. Yeah? Alright, so let me just give you a summary of what we have done. So, in today's lecture, the most important thing that you need to know is how to test general linear hypothesis about beta. The rest are also important, but the most important one is this one. And this extra sum square method that I described in the last lecture is a special case of this. And I've shown you quite a number, many examples to illustrate this general linear hypothesis about beta. So let's take 5 minutes break, and then we'll continue with tests of confidence interval and estimation and break.
So can you explain to me why like it doesn't do like beta 1 and beta 3?
Okay, welcome back. Let's continue. I still have 3 more little topics to complete. So next, I want to talk about test and confidence in on individual regression coefficient, estimation of mean response, and prediction. So that's what I want to do. I hope I can finish it in half an hour. Should be okay. If I don't finish it, you read on your own. Well, so let's start with the multiple linear regression model here. And as usual, we have k plus 1 regression coefficient, beta naught, beta 1 up to k. There are only k regresses. And we assume that this is normal, because if you want to do testing, you need to assume a certain distribution, and that's our assumption. Now earlier, I have already shown you that expected value of beta hat is beta. So the really where estimates of the regression coefficients are unbiased, and the variance is sigma square times this matrix here, x prime x inverse. I am going to call this matrix C. This matrix C is the inverse of the x prime x matrix. So from here, we know that this is the variance of beta naught, and this is the variance of beta 1 hat, multiplied by sigma square, of course. Yeah. So sigma square times ckk is the variance of beta k. And the off-diagonal elements are covariance. So this is the covariance of beta 1 and this one. So this is the covariance of beta naught hat and beta 1 hat. Well, of course, we can estimate this using a hat. So that's what we have. So according to linear model theory, again, I'm not giving you the proof yet. You do some of this in tutorial. Maybe some in exam, I don't know. I will set the exam question. So we know that beta j hat minus beta j divided by the standard deviation of beta j. I told you already, right? This is the standard deviation, sigma square. Let me just move it a bit. Sigma square hat Cjj is the variance of beta j hat, which I've shown you here. I don't know what happened to that. My hand is still sticky here. And so this is a fact that you need to assume for now, which will be proved in tutorial, I believe. Now for testing, suppose you want to test individual regression coefficient, beta j equal to C versus beta j is not equal to C, then this will be our test statistics. We will reject the null hypothesis if it is, suppose here's a t distribution is 0. This is alpha over 2. This alpha over 2. This value is this value. This is this. So that's how you can do testing, or you can construct confidence interval. Now, from step 2 to step 3 and 4, I assume you have learned it. Okay? That's why I'm not explaining why this is so. Once you know the distribution, you can develop the test and you can develop this confidence interval. Either you learn it in probability or you learn it in mathematical statistics. So if you do not know how to do it, go home and revise it or Google search it. Now, all these are useless if you don't know how to apply it. So in R, constructing confidence interval is very simple. Testing also very simple. So to test individual regression coefficient, summary is the function to use. To construct confidence interval, confidence INT, CONF INT is the one to use. So let's look at an example. So here, I have still based on the PR2103 data, I have a summary of the model. So here, you can see I am doing t-tests here on each one of them, whether they are different from 0 or not. Okay? So you can see that they are all very small, except for beta naught. So they are all significantly different from 0. And here's the confidence interval. So if you apply this, invoke this function, you will get that. So now let's go to estimation of mean response. Now in simple linear regression, we have gone through this. But now we are going to go through this for the multiple linear regression setting, which will include the simple linear regression case. So point 1, according to my note, we have this model and the usual assumption. And point 2, I have written it, not in the matrix notation now, but in terms of the usual equation. And then consider a particular set of regressor values here. This one. It means I consider this value. And then there's a 1 here. So x0 refers to a set of regressor values. Let's say it's x0. And then y0 is the response for this regressor set of regressor values. Okay? So the response is this. So I've written this set of regressor values as a vector. Now what I want to do is I want to estimate the mean of the response at this particular set of values of the regressor variables. Now the mean can be found easily by taking expectation of this, which means expectation of this. Expectation of this is 0. So that's 0. And the expectation is just beta naught plus beta 1 x1 and so on. And this can be written in matrix notation. X naught prime times beta. Okay? Now what about the fitted value? So we now know what is the mean. This is the quantity that we want to estimate, that we want to construct confidence interval. It is a linear combination of the betas for this set of regressor values. Now the estimate for this mean is this one. We just substitute all the betas with the estimators, yeah, beta naught hat and so on. So we are going to use this to estimate this. And it can be shown in matrix notation here. Alright? So, first of all, 0.5 now. Note that this fitted value is a function of y, so it must be normally distributed. And we are estimating the mean with y naught hat, as I have pointed out here. Yeah. So I am going to estimate that. And the mean of y naught hat, the mean of y naught hat. So what's the mean of y naught hat? Well, let's try to calculate it. The mean of y naught hat is expected value of these two vectors. So you can take out x naught out and take expectation of beta hat, which is this. So this our estimator. So we are going to use this to estimate the mean. And of course, we want our estimator to have the same mean as the mean response. So that is proved in item 7. Now in item 8, I should now try to find what is the variance of y naught hat. You see, we are using y naught hat to estimate the mean response. So we need to know the mean, we need to know the variance. The variance, I have given you some formulas on operating on variance of matrices. So the way to do it is you have x naught prime, x naught, and the variance. Here, refer to my earlier notes in chapter 3a of B. And this variance of beta hat is this one times this one. Yeah, like what I have described earlier. So, but this is an unknown, sigma squared. So in order to be able to construct confidence interval, we need to be able to estimate it. And that's why there's a hat now. So this is an estimate of the variance of y0 hat. So everything is now known. So I know the mean, I know the variance. I can now use linear model theory to show that this quantity, y naught hat is our estimator. Subtract the mean, divide by the standard deviation, it will follow the t distribution. Yeah? So this you prove in the tutorial. And because of this, you can now construct confidence interval. You can track this quantity between 2t percentile, and then finally arrange to have the mean response at x naught at the center. So this is a derivation of the confidence interval that I'm talking about. So you can go through this process for regression coefficient. It's the same procedure. and then you can find this confidence interval. Okay? So it is this. So what are we estimating? We are estimating the mean response at a particular set of values of the regressors. So let's look at the delivery time data. I want to construct a 95% confidence interval for the mean response, not for the mean time to complete the job. If I'm delivering 8 cases and the distance is 275 feet. So what you need to do is create new data with this set of regressor variable values, and then use predict, and then say you want confidence interval, you'll be able to get it. So this particular page, I got it from the book, only this page, but I don't think it's of any use, except that it shows you how to do it manually. But I think it's good to read it just one time, to understand it. Because when you use R, a lot of things are gone. So I advise you to read this particular page from the textbook and make sure you know what it means. So you can, so for us, all I need is 2 statements, and I'll be able to find a confidence interval for the mean response time at this value. Okay? Now, let's go on. We have also talked about prediction of new observation. And this is important. One major use of regression is prediction. You want to predict whether this stock will go up tomorrow or not. If you think it's going to go up, put everything in. If you think it's going to go down, sell. Even if you don't have. That's called short sell. Hopefully it won't go up. If it go up, you go bankrupt. So, suppose we have a multiple linear regression model. Same type of condition. Again, the most important assumption is this one now. Assume that the error vector follows a multivariate normal distribution. This model, again, can be written in a non-matrix notation. It's the same as before. And now, I want to make a prediction of y based on these regressor values here. Yeah? For a particular value of x1, a particular value of x2, and so on. And I call it x0, x0. So this is what will happen if you observe it. If you observe it, that is y0. And there's a random error. Okay? The random error will make this y0 a random variable. So now we are trying to predict, not a constant, unlike the previous case, mean response is a constant. We're trying to predict what this is, a future observation. So, how do we predict? Well, if you have fitted an equation, all you have to do is to plug it into your multiple linear equation, and you can predict it using the fitted value. And that is written here in matrix notation. And to construct a prediction interval for y0, you need to consider this particular random variable. Okay? So let's look at this difference between y0 and y0 hat. Now both are random variables. And the expectation is 0 because both expectation give us the same value, x0 prime beta. Now what about the variance? The variance of the difference of two random variables is the variance of y0 plus variance of y0 hat minus covariance. Now this is 0 because the future observation is not going to depend on your predicted value. The future observation is completely independent of your prediction. Put it this way. That's why making money using prediction is hard. Because whatever you predict has nothing to do with what will show up. Okay? Seems a paradox. Huh? But, so, what is variance of y0? Sigma squared. What is variance of y0? Y0 hat? So this is sigma squared. This one, we have gone through it just now. This is the variance of a predicted value, or fitted value. And so we have the variance also. And of course, the variance depends on some population parameter. So we need to estimate it. You can estimate it using the mean square residue. And once you estimate it, you put a hat. So that's the estimated variance. So for linear model theory, this quantity, y0 minus y0 hat, minus the mean, divided by the standard deviation, follows the p distribution with n minus p degrees of freedom. So, I did more of this type of derivation in mathematical statistics. I don't remember whether I did it in probability or not. Because in probability, we study how to find all sorts of probability. But the idea is not too hard to understand, even with probability knowledge alone. We have a random variable. I want to track this random variable within two values. Here's a t with n minus p. So I track it at this value, alpha over 2. This is t minus t alpha over 2. So the probability that the random variable is tracked between these two values will be 1 minus alpha. So you form an equation first, and then you try to arrange so that y0 is now in the middle. Remember, y0 that we are able to track here is not a constant. It is a random variable. That's why we don't call this confidence interval. We call it prediction interval. Because we are trying to track a random variable. So that's the difference between confidence interval and a prediction interval. Prediction interval is an interval for estimating a future observation and a random variable. So you can then use this as your prediction interval. So everything can be found. Yeah? So 0.9, 0.8 tell us exactly the same thing. So if we are trying to find an estimator, an interval estimator for the mean. For example here, the mean of y given x naught, then is confidence interval. If you are trying to estimate a random variable, is known as a prediction interval. And again, all these theories are very beautiful, but remain useless until you can use it. And R give us a way to use it. So suppose I want to find a prediction interval. Well, what that means is this. I'm doing the delivering job. And then there's a new location coming up. I've not done that before. Yeah? And I know that I have to deliver 8 cases. And the distance is 275 feet away. So before I go, I want to plan my route nicely. And I want to just find out, I want to make a prediction. How long am I going to take to complete this job? This one, prediction interval is all about. So in this case, it is a future observation. And I want to have an idea how much time it would take me. So I set up the regressor variable values here, call it new data, and then feed the model, use the new data to construct a prediction interval, a 95% prediction interval. And then that will help me to make a prediction. Again, this one is from the textbook. I want to stick close to the textbook so that after my explanation, if it's not clear to you, you can go back and refer to the textbook. I could have used 3 or 4 textbooks, but it will be very hard for you to follow. That's why I stick to one closely, so that when you go back, you miss something I say, you can go back to the textbook and refer to it. I have so many textbooks I can refer to, but I choose one good one for you. Alright, so here's from the textbook. Go through it. Make sure you know how to do prediction interval by hand. Who knows? It might show me an exam. I don't know. I haven't said it yet. Next week I will. So, for R, so this is by hand. As you can see, it's quite laborious. But I think it's good to know how it is done by hand, just for once. When you go to work, you are not going to go through this because it's very tedious. All you need to know is how to set up a new data that contain your regressor values, and then call this function predict, new data prediction. So now I know this time so I predict the time that I'll take is about 19 minutes or whatever, 19 minutes. And the prediction interval is somewhere from 12 to 26. So I have an idea. I should be able to do the job, at most, or, quite likely, 26 minutes, I should be able to get it done. Very likely. And my prediction is 19 minutes. Okay? So let's do, my alarm has not sounded yet, so don't worry, it will come. If it doesn't sound, that means there's no quiz. Huh? So, it has not sounded. Let me do a review. So today, we are testing general and linear. These are the keywords. So we're going to test linear combinations of vectors and multiple, a few of them at one go. And it's general. So we are not just testing beta 5 equal to 0, beta 6 equal to 0. If I only testing the last two equal to 0, then it's called, I can use the extra sum of square principle. But here, sometimes I want to test whether beta 1 is equal to beta 2 or some combination. Yeah. And so, this extra sum of square is special case of this. And then we have, I talk about test and confidence interval on individual regression coefficient. So you need to understand the X prime X inverse matrix, because that tells you what your variance is. And then we also talk about how to estimate mean response. And finally, prediction of new observation. After all, there's a quiz, okay? So let me turn it on. Let's see if I can turn on with my phone. I have 3 different ways to do it. I guess the phone version is not good enough. Okay, it's up now. What you need is the question. Today's quiz is based on today's lecture, as usual. So I hope you have paid attention today. Let me just, okay. I think that's fine. So once you are done, you can get up and go.